So let me start. So the topic I'm going to present today is low carbon clinkers derived from solid waste. My name is Dr. Shipeng Zhang, an assistant professor from the Hong Kong Polytechnic University. This is the table of contents for today's talk. I will briefly introduce the background of my research. Then I categorize cement into two categories. First one is low carbon cement with carbonation reactivity and low carbon cement with hydraulic reactivity. Then conclusion. Okay, so very brief background. We all fully aware that the gases with CO2 generation has been significantly increased over the last few decades. This is a trend in global CO2 emission from IPCC. And this is the major contributor to global warming, sea level increases, more frequent, more impact, more intensity, different extreme weather events such as flood, wildfire, tropical storms, etc. I don't know why I have autoplay. This is why the General Secretary of United Nations, Mr. Antonio, stated that we are on a highway to climate hill with our foot still on the accelerator. And unfortunately, the material or the field I'm working in, the concrete material, is the major CO2 contributors. Second only to water, concrete is the most consumed material. And of course, it's the most frequently used building material in this world. Yeah, typical concrete, we have 6% of air, 11% of Portland cement, 41% of coarse aggregate, 26% of fine, and the rest is water. So among those ingredients, Portland cement is the most carbon-intensive component, which due to two reasons. First of all, we need high temperature to synthesize Portland cement. The major mineral phase in Portland cement is C3S, and we need 40-50 degrees C to get this phase. Although we already try to lower down the temperature by adding different fluxing agents, but 40-50, that's the best we can do right now. The second major contributor during this production process is the decalcification process of calcium carbonates. Because Portland cement is calcium-rich material, we need calcium. And the raw material is calcium carbonates because this is selected by most of the cement plants because it's relatively cheap and doesn't have regional limitations. But at a high temperature, over 800 degrees C, calcium carbonate will intend to decompose into calcium oxide, which this is what we need, and CO2. So that's why 70% of CO2 emission from cement production is attributed by this decalcification process. In general, to produce 1 ton of cement will approximately generate 1 ton of CO2. It's 1:1 ratio. That's why this single material contribute 8% of total anthropogenic CO2 release in this world. And when we talk about cement, we normally refer to hydraulic cement, which means by that is that this cement will react with water, H2O, and develop strength. So this C3S reached OPC, Portland cement, has been changed since 1824. So in our research, we are thinking that, okay, maybe we can change that. We can make some novelty move from the mineral composition perspective to lower down the embodied carbon. That's why we create a carbonatable cement, because the cement itself is not only has hydraulic behavior, it actually has carbonation reactivity, which means that cement can only react with water only. It can also react with CO2 as well. We call it carbonation. During this process, CO2 can be transferred into calcium carbonates. We call this process CO2 mineralization, because calcium carbonate is also called limestone. It only, like I said, it only decomposes under high temperature, greater than 800 degrees C. So it's very stable. And in normal condition, we call it permanent CO2 capture and sequestration. So in summary, when we talk about low carbon clinker or low carbon cement, we need to lower down the clinkering temperature. We need to low carbon raw material, ideally from waste. And ideally, if this material can actively capture and sequester CO2, that'd be perfect. So this becomes our objectives. We utilize different type of solid waste, most of them locally sourced, either from Hong Kong or mainland China. Then we go through a feed design. because the raw material we choose, those solid waste, mainly consists of calcium, silicate, aluminum, iron, or sulfur. That is exactly what we need in our cement clinkering process. During this feed design, we also get help from thermodynamic modeling to guide our design. Then we do the mineral phase clinkering. We categorize our products into two categories. First of all, is mineral phases that can be triggered by CO2. My candidates including C2S, C3S2, CS, and CE. CE stands for chloroelastinite. So those are the mineral phases that can be synthesized at less than 1,200 degrees C. It has lower demand on calcium and strong carbonation reactivity. So we meet our criteria or the requirements the target we set to ourselves before. The second category is mineral phase triggered by water. So it's hydraulic cement. The potential low carbon mineral we choose is a combination of C2S and CSA. Again, it doesn't need high temperature, lower clinkering temperature, rapid early strength, and by adding C2S and CSA, we can control the expansion risks which is an inherent problem for CSA cement. Okay, so we have different types of candidates of cement. Okay, so first one, low carbon cement with carbonation reactivity. The first solid waste we target is called municipal solid waste incineration ashes. So municipal solid waste is a residential, light industrial, commercial, and institutional waste that we generated every single day. Worldwide, this waste is one of the major solid waste streams. In Hong Kong, we generate 3.96 million tons of MSW every day, and every year. And all of them are ended up in landfill sites. In Hong Kong, we have 3 strategic landfill sites, and all of them are reaching their capacity because land, everybody knows that in Hong Kong is very expensive. Now, the Hong Kong government is building an incinerator, basically burn all the garbage away. That is also the most popular way to treat MSW because we can reduce the volume, weight, and reduce hazardness of the waste, effectively remove pathogen and organic during this process, prevent the production of methane, and we can actually collect energy out of it. But this is still not the final solution due to the generation of IBA and IFA, around 25 in total, 25% of the original weight of MSW. I won't go to too much details on this, but in Hong Kong, we are going to have a new incinerator start commissioning in 2026. And this is phase 1, and we plan to have 3 phases in the future. And in the near future, we're gonna have more than 2,000 tons of IBA generated, and more than 500 tons of IFA generated every day. And the current plan again is landfill. In mainland China, incineration is more mature, more than 583 incineration plants, and generate IBA 36 million tons per year, IFA 9 million tons per year. So it's a huge amount. People trying to utilize IBA and IFA, but there are a couple of challenges, including heavy metal leaching, aluminum-induced hydrogen gas generation, low value for IBA, or for IFA, we don't have a good solution yet. Okay, so that comes to our first clinker. We use IBA and IFA. We use IBA to supply calcium, silicate, aluminum, and iron. IFA is a major supplier of calcium. Through raw feed design, the solid waste in raw feed is greater than 93%. This design parameters, including those traditional design parameters in cement making, lime saturative factor, aluminum factor, silica factor, splicing content. And we've also done the thermodynamic modeling I'm going to show you in the next few slides. Then the temperature is around 1,100 degrees C, which is much lower than 1450 degrees C. But here I need to make a small note that when we talk about temperature, the energy consumption of energy by increasing the temperature from 1,000 to 1,400, the energy consumption is exponentially increased. It's not simply linear correlation. It's actually exponential correlation. Okay, and the primary phase we successfully synthesize the C2S as CE. CE is a quite normal mineral phase that's only reported by us in binding material is colloelastinite. It has a very high carbonation reactivity and latent hydraulic behavior as well. We call it low carbon because low carbon raw material, because in IB and IFA, we went through a high temperature, so the carbon embodied of them is very minimal, and low cleaning temperature, and they can achieve carbon capture. I just give very small details about thermodynamic modeling with it. So first of all, we use Facet and to calculate the Gibbs free energy for different phases to figure out what are the possible phases in our system. And then we selected different composition of calcium, silicate, aluminum ion, and using that to indicate the generation curve of different phases. This we choose 4 different raw mineral composition, chemical composition. Okay, and we choose the one with the highest C2S. That's the target phase for now. And this is we zoom in and we calculated the mass content of different phases in our system. We calculated the viscosity at high temperatures. From that, we can calculate the reaction activation energy for each reaction, particularly for C2S. Okay, then because we use solid waste, so there's a lot of foreign ions in the system. So here we modeled how those foreign ions, including sodium, magnesium, etc., to how those foreign ions are gonna affect our clinker phase generation. Okay, so we dope different dosages of foreign ions. Then we choose the best from modeling, and we use real clinkering to identify our results, and it shows relatively good correlation. And these are the results. So for clinker 1, we successfully synthesized this clinker with C2S and Ce. And we have 2 different directions of using it. First of all is we use it as sole binder. So we use that cement as 100% to replace OPC. And we found that through compressive strength, this material has a hydraulic behavior, so it can react with water only, but it only achieves relatively low strength compared to our reference OPC. This is commercial OPC. So after 90 days of hydration, it can only achieve 33 MPa compared to 56. But if we can do carbonation, the strength of the eco cement significantly increased up to 67 MPa compared to 62. This is carbonated OPC. Like I said, OPC can be carbonated as well, or we can see strength enhancement as well. So it reached a slightly higher strength than OPC. So we confirmed the feasibility of using it as 100% of low carbon cement. And we did a series of durability tests. So we want to figure out how it behaves under service life. This is a typical one we choose. It's freeze-thaw resistance. Freeze-thaw is not a problem in Hong Kong, but since this project was done in Canada freeze-thaw is a huge problem. We use mass retain to reflect the damage severity of our sample. After 30 cycles of freeze-thaw cycles, all the reference batches all dissolved, and the mass retain becomes 0, which means all the concrete dissolved, like in the water. But using our material and through carbonation, we found that it's barely damaged after 30 cycles. So it shows a very good durability performance. And the second direction is that we use our material as a replacement of OPC as a supplementary cementitious material. So in this system, we use 15% of low carbon cement and 85% of OPC. And we found that for hydraulic behavior at the very beginning, the strength decreased due to dilution effect because we have less OPC. But if we do subsequent hydration, the strength can be increased and achieve the same level of OPC at 90 days. And we do have the luxury to do carbonation, because for carbonation, we need to have a carbonation chamber. We need to pure CO2. So it involves some capital cost. And we know that not everybody has a luxury of carbonation chamber. But if we do, this blended cement achieves the highest strength compared to other batches. The freeze-thaw resistance test shows a similar results that if we do carbonation using our material, it can achieve a very high freeze-thaw resistance compared to our reference batches. For microstructure, it shows a quite unique microstructure. The CE particularly, this normal mineral, can be active by CO2 and forming a cluster-like microstructure. And simply those clusters can keep growing and densifying itself. This is 28 days and this is 90 days sample. So during this, between 28 days and 90 days, those clusters kept growing and densify itself, forming a very, very dense microstructure, which is the reason for the high resistivity and high compressive strength. Since we use solid waste, we ran a very comprehensive environmental analysis, including heavy metals, leaching, pH, dioxins, and furans, and VOCs for clinker and concrete made by clinker. So it's all passed the criteria. And the second solid waste we involved in this project is recycled concrete fine, because at the very beginning we used IFA to supply calcium, but IFA doesn't have a very high generation amount in Hong Kong, but RCF does. In Hong Kong, RCF's content is 3,000 to 6,000 tons per day. And this is a byproduct from the recycling process of waste concrete. For coarse waste concrete can be used as aggregate again in new concrete making, road construction, etc. But during this recycling process, we have a very fine powder left that can be reused due to the fact that those materials can involve new microcracks to the system, weak interface transitions, high water absorption, etc. So it's detrimental to new concrete, and most of them are disposed at landfill right now. And in clinker 2, we target using IABA and RCF to supply different ions. In this side, the solid waste is greater than 85%. We played around the temperature more closely this time, and because we realized that C2S can give us a very high strength, so in clinker 2, we only focus on C2S. When we vary the temperature from 1000 degrees C to 1200 degrees C, the beta C2S and gamma C2S content varied. Particularly at 1100 degrees C, the beta C2S content becomes the highest, around 45%. And from the compressive strength results is also reflected the mineral composition variation. The batch at synthesized at 1100 degrees C, the strengths behave the best. So after 1 day of carbonation, the strengths achieved more than 110 MPa, which is a very high value compared to our reference OPC, commercial OPC reference is around 40 for 28-day hydrated and 28-day carbonated, which is 60. So we almost doubled it. And we also found the strength increased for this batch, phenomenal for this batch. And at 28 days, it achieved over 130 MPa, which is a very high value in terms of strength. And through several graphmetric analysis, we calculate the CO2 capture rate. And the capture rate is ranging between 10.2 to 15%, which means that 100 grams of cement we synthesized can sequestrate 10 grams to 15 grams of CO2. OPC, for OPC, this number is 8%. And this batch, 1100 EC1100, that's behaved the best in terms of compressive strength. And we found that it doesn't have to be a linear correlation between the strength and the CO2 capture rate. The fact is that the reason is that beta C2S is actually can give more strength, while gamma C2S can absorb more CO2. So the coexistence of beta and gamma C2S cause the differences in CO2 capture rate. And the reaction products also we found that the coexistence of polymorphs of calcium carbonates, waterite, and calcite. Gamma C2S, when it reacts with CO2, it forms waterite, while beta C2S will form calcite. And different mineral composition exhibit different mechanical performance. So we have to have this balance between the strength gain and also CO2 capture rate. When we need higher strength, we higher the content of beta C2S. While if the target is to absorb more CO2, we increase the gamma C2S. That can be controlled through our raw feed design and the clinkering process. Okay, then this is the nano indentation test that we conducted to evaluate the micromechanical performance. And again, the EC1100 batch behaved the best, recorded the highest value in terms of elastic modulus and micro hardness. The reason is that when the carbonation of beta C2S occurred, beta C2S will generate low calcium CSH, calcium silicate hydrate, while gamma C2S will generate silica gel after carbonation. In terms of micromechanical performance, CSH, when we have calcium in the system, is stronger than silica gel because the bonding between calcium is stronger. Okay, and that's caused the differences in micromechanical performance. This is a porosity. It shows the lowest in porosity as well. And we ran the leaching TCLP once we run one leaching test for our material, and all 8 regulated heavy metals were well below the regulation numbers. Okay, then we further pushed this test, this technology from lab to pilot scale demonstration. We mass produced the clinker using the industrial scale kiln. Okay, that's mass produced clinkers. Then we retrofit autoclave chamber into carbonation chamber. So we basically inject CO2 instead of steam in this setup. Then we produce a couple of batches of full-size CMU, concrete masonry units. And we found that each unit, which weight in average is around 17 kilograms in weight, can sequester 294 grams of CO2 in each block. And we tested the strength, density, absorption, and linear shrinkage properties of this full-size CMU is all well satisfy the local standard. We did this in Ontario, Canada, with the help of emerald, beamer's block, and carboclave. We use our eco-cement as sole binder, so 100% of eco-cement. In this case, we produce a potassium rod using our material, using our blended cement, so 15% of eco-cement plus 85% of OPC. We laid this potassium rod just in front of an incinerator. There's an incinerator. We want to showcase that the residues came out of this incinerator can become a very nicely done potassium rod. This rod has been there for a couple of years. Okay, then clinker 3. That's another quite novel mineral phases we developed here in PolyU called chloroelastinite. Chloroelastinite has been discovered in nature. Is classified underneath the apatite supergroup. Apatite supergroup has been widely applied in environmental remediation material. It has the capacity to immobilize heavy metals. Okay, so because it's below this category, we guess that it has a similarity in framework to apatite, so maybe promising immobilization material. CE has been formed and discovered in cement production process. In mainland China, this is the process called co-processing. Basically, they burn the garbage with cement kiln. That's and what will involve different foreign elements such as chlorine and sulfur. That is basic for chloroelastinite. And the people discover that in the inner surface of kiln, but nobody has ever worked on it. So before application, there's several questions we ask ourselves is that what's the nature of CE? How does CE behave at carbonation curing and hydraulic curing? Is it going to be a potential SCM or binder? So we synthesize CE in the lab. We synthesize a pure CE. It's longitudinal, it's like this, the crystal shape, longitudinal rod-like crystals. And the purity of CE we synthesize is higher than 96%. And we did the carbonation and hydration test on it, and we found it only has a very slight hydraulic behavior, around 5 MPa after 28 days. But if we let CE interact with CO2, the strength significantly increased to more than 30 MPa. So it shows that it can have a potential to be used as SCM or binder. We did mineralogical analysis using QXRD, quantitative X-ray diffraction, NMR, and the morphology through ICCEPM. So basically, we came up the carbonation reaction formula. This is CE. When you interact with CO2 with accompanies water, it forming gypsum, calcium gypsum, calcium carbonates, and calcium chloride and silica gel. Actually, it decomposed into calcium chloride, which is not that good because chlorine is problematic when concrete involve reinforcing bar, when steel bar. So chlorine can trigger the durability issue. So this material can be used, but only used in concrete without reinforcement. Okay, then we try to apply it as SCM. We use OPC plus CE with a dosage ranging from 0% to 40%. And we found that this is strength. At 1 day, the strength decreased. Up to 7 days, it's also decreased with incorporation of CE. But at 20 days, the strength enhanced. This is particularly interesting is that through morphology analysis, we found that the atringite, which is a common mineral in OPC, significantly growth in the matrix in this batch. This is the atringite, which is supposed to be a very thin needle, like this. But this is the atringite looks like in the blended cement. We found that the atringite crystal, not only the length of it, the diameter of the crystal was significantly increased. This is due to the fact that during the carbonation of CE, gypsum generated, this secondary gypsum will promote the atringite formation. Okay, and this microstructure refinement will lead to the decrease in this MIP, which means the porosity of the matrix. So it decreases in porosity, lead to the high strength. Okay, this is another category as the low carbon cement with hydraulic reactivity. The solid waste we use here is phosphogypsum. Phosphogypsum is a byproduct generated during the wet process, phosphoric acid production. It has, we don't have this flow waste in Hong Kong, but it's quite problematic in mainland China, in those provinces. And right now, only less than 15% of phosphogypsum was recycled. Because the fact that it has a lot of heavy metal containing in phosphogypsum, it has a lot of fluorine leaching from it, soil pollution because of that. However, actually, heavy metal and fluorine is good fluxing agent in cement making. What this fluxing agent means that it can reduce the melting point temperature of my raw material. So it reduces the temperature required in the kiln. So it's actually good for us. Okay, so we use IBA, RCF, and phosphogypsum, okay, to become the raw feed. And the design parameters, LAF, it's different. It's specifically for CSA. Then we tried, the temperature is ranging from 1100 degrees C to 1300 degrees C. We successfully synthesized baelite-rich yeelimite clinker. Yeelimite is CSA. In the market, yeelimite or CSA cement is quite expensive. The reason is that although it considered a low carbon cementing material, CSA, it has a quite unique feature because it can harden very fast. So CSA has been widely used in practices such as if we want to fix the road quick, for example, quick construction when you use CSA. But the thing is, it's very expensive due to the fact that aluminum bearing raw material is very expensive. But here we use IBA and MCF. Okay, so in this batch, in this cement, we have beta C2S content 46%, yeelimite is 23%. And through mineralogical analysis using QXRD, yeelimite, ternocite, fluoroelasticite, and beta C2S all of them can do hydraulic behavior. We target beta C2S before in the previous category for carbonation reactivity, but the fact that beta C2S has also have latent hydraulic behavior. The fact that it cannot be used in hydraulic clinker is that it has latent hydraulic behavior. It takes time for this mineral to react. The main hydration products including AFT, itringite, and CSH gel. The network formed by AFT as I promised the strength development. So as I mentioned before, those needle-shaped itringite is itringite, needle-shaped crystal is itringite, RR itringite. Well, it's intermixed with CSH gel. Actually, itringite is a very good crystal. It has a very strong crystal strength in terms of micromechanical performance. However, it's quite weak for weathering carbonation. It's weak when it's sensitive to CO2, atmospheric CO2, so it can be decomposed. C2S, why we have C2S here is that why we design C2S is to protect the strength decrease from itringite decomposition. Okay, this is the compressive strength of the cement we produced. That's 1,100 degrees C. That's 1 day. Then we achieve basically we achieve the same level of strength with compared to commercial CSA cement at 28 days. Okay, so in conclusion, a series of cementing systems were developed from solid waste. A clinker demonstrated a strong CO2 reactivity and/or hydraulic behavior. This low carbon cement exhibits superior mechanical durability and environmental stability, and carbon footprint was reduced by 3 aspects. First of all, low clinking temperature. Second, low embodied carbon raw material. Third, carbon sequestration. And our dream is to convert the city into mega CO2 sink. Every single building can sequester thousands tons of CO2. Okay, and the last point is pilot scale that has validated the feasibility of producing and applying low carbon cement at a larger scale. Okay, thank you very much. If you have any questions, I'm more than happy to answer that.